Hey folks, welcome to this episode on Ionic Nomenclature and Formulae. So we saw this chart before. We were first looking at the molecular naming and formulas, and today we're going to be looking at the ionic section. Now we're first going to start off with cations or metals that only have one charge, and then we're going to expand into them having more than one charge. These ones are called multivalent metals. So remember that ionic bonding is caused by the transfer of electrons and results in a cation and anion, and there's an electromagnetic attraction between that cation and anion. Okay, there's an attraction between those. And when we form this kind of compound, what we get is a formula unit. And remember, that's kind of just a repeating pattern of sodium and chloride, and these constantly repeat. So it's the lowest whole number ratio of this kind of repeating unit in this structure. So again, what we have to do when we're talking about ionic is figure out whether the metal, or the cation in the case, has only one charge or it has multiple charges. If it has only one charge, it really is a little bit more simple, because we don't have to use the Roman numerals that we have to use in here to show what the charge of the metal is. We can just do straight naming, which means that we can just name the first name, change the last name ending to "ide," and be done with it. Once we get into ones that have more charge, or the multivalent metals, we're going to have to use Roman numerals to show what charge the metal has. So this looks a little bit daunting, but it is quite simple. The cations, or in this case the metals, always go first and the anions always go last. What we want to figure out is what is the charge of the actual metal. And so we can look to the periodic table to figure that out. Now, in this case, if it's in group number 1, it has to lose one electron, kind of skip to the left, so it's become 1+. If it's in group number 2, it's going to lose 2 electrons to become that noble gas configuration, so it's going to be 2+. Another way of kind of remembering it is that if you go 1, 2, 3, skip, and skip would be 4, and then you go 3, 2, 1. Now, the noble gases don't bond, so that they won't be part of it. So in this case, if it's a metal, it's going to be plus. If it's non-metal, it's going to be minus. So you have 1+, 2+, 1+ over here, 2+ over here, 3+ over here. These will have 4+ or 4-, depending on what they're bonding with. 3-, 2-, 1-, and these don't count. So you can use that, but really understand why they do that. And that's again caused if we look at fluorine, it only has to gain 1 electron to become a noble gas configuration. Oxygen has to gain 2 electrons to become a noble gas configuration, etc., etc. So once we figure that out, write the oxidation states on top of the element and down cross. And we always want to simplify, so that means that we either reduce, if there's a common factor, we reduce it, and if there's ones, well, we don't write them. Okay. If you're talking about polyatomic ions, which we've previously done, and we're going to be talking about them now, if their subscript goes around a polyatomic ion, XX, and it's greater than 1, for example 2, we're going to need brackets, because remember that polyatomic ions act as a single unit. So in this case, let's do some example. Here we have lithium and nitride, lithium nitride. So the first one is lithium, okay, and the symbol for lithium is Li. Okay. The symbol for nitrogen is N. Now it's ide, which means that it's just a regular element, not ate. It's not nitrate. So we have to first look at lithium, see what charge it is. So if we go to our periodic table, lithium is right over here. It's in group number 1, and it's a metal, so it's going to lose 1 electron. If it loses 1 electron, it becomes 1+. Now nitrogen is right over here, right there. And because it's a non-metal, it's going to want to gain electrons. Now, how many electrons does it have to gain? It goes 1, 2, 3 to get to that noble gas configuration. So if it gains 3 negative charges, it's going to be 3-. So we take these charges and we cross them down to opposite sides. And so we'll get Li3N1. However, we simplify, so we don't write this 1 over here. Okay, so what we're going to see in the end is Li3N. Now, aluminum sulfate. You might see a little bit different. That is the British way of spelling aluminium sulfate. So the first thing is we need to know what the symbol is. Aluminum is Al. And here you have to be careful. It's not sulfate. It's not sulfide. It's sulfate, which is a polyatomic ion, SO4. Now, what's the charge of aluminum? Well, if we look to aluminum, aluminum is right over here. It's in group 3, and it's a metal. So a metal will lose. It's going to lose 1, 2, and 3 to become a noble gas. So that will be 3 plus, not to become a noble gas, but have a noble gas configuration. Now sulfate we can't find on the periodic table, that just has to come from memory. Sulfate has a charge of 2 minus. So now what we're going to do is we're going to cross these down. This one will go on the outside of SO4, and this one will go by Al2. So Al will have 2. Now we'll have SO4 3. Now in this case, if we were looking at it this way, without brackets, 3 would multiply by the 4, and we would have, when you multiply these, you get 12. So we'd have S1O12, which is not the case. That 3 multiplies everything inside these brackets. So we're going to need to have that. So now we have 3 sulfurs and we have 12 oxygens. So we can't simplify this any further. This is our final answer. Our last one here, calcium oxide. Calcium is Ca. Oxygen is O. Now again, we need to figure out what the charges are, so we look to our periodic table. Calcium is in group 2, it's a group 2 metal. That means it's going to lose 2 electrons to become 2 plus. Oxygen is in group number 6, and it's going to gain 2 electrons because it's a non-metal to become a noble gas configuration. So that means it's going to be 2 minus. If we cross, we get Ca2O2. But wait a second, you can see that both of them have the same common factor, 2. So we can actually factor that out and be left with CaO. So go ahead, stop the video, and try to come up with the formula for these following names. So stop it, we'll come back with the answers. Alright, welcome back. These are your answers. There shouldn't be any tricks here. The only thing that you have to remember is that if your outside subscript is 1 around a polyatomic ion, you don't need to use the brackets. In fact, don't use the brackets. You only use the brackets if that coefficient or the subscript is greater than 1. Now, in terms of naming them, it's even more simple. We first have to figure out if they're ionic. If we know they're ionic, metal and a non-metal, we now have to check if the metal is multivalent. If it has more than one charge, and usually those are found in the transition metals, we're going to have to use a special set of rules. But if it's in group number 1 or group number 2, or if it's aluminum, it's going to be multivalent. There's also a couple other exceptions. So if it's group number 1 or group number 2, or if it's aluminum, zinc, and silver, there are a couple other exceptions, but those will always be monovalent. So if you look for those, then your naming is going to be very, very simple. We always look at the cation going first, anion going second. The only thing is that we name the ending of the nonmetal, the second one, we change it to "ide." And one thing to keep in mind is that polyatomic ions, they always keep their endings. They don't change to "ide." So here we have a couple ones. So right away we can see we have our exception. We don't need to use any kind of fancy rules. Zinc is one of our exceptions. So all we have to do is name the first one as is. So Zn is zinc. And the other one is oxygen, but we change the ending to "ide. So we have zinc oxide. Done. Second one, we have AlCO3. So Al is aluminum. So aluminum. And the second name is CO3, which is carbonate. Now remember, it's a polyatomic ion, so it's going to keep its ending of 8. And that's it. So stop the video and practice these ones, and we'll come back with the answers. So go ahead and pause the video. Alright folks, welcome back. Here are the answers. So just check, make sure that you have everything right. Just be conscious about the endings. Now that we've seen the polyatomic ions, don't get confused with the endings. If it's a simple element, it will still end in "ide." If it was PO4, then this whole formula would be changed, but that would have an ending of 8. Now, multivalent metals. So a lot of these transition metals are capable in combining in different formats or in different proportions, and that's because they can have different charges. These are called multivalent, so they have multiple valencies or multiple charge cations. When we deal with these metals, we have to use the Roman numeral system to figure out or to tell our reader what charge it has. So for example, in here, manganese can have a 2 plus, 3 plus, or 4 plus charge. How do we know which charge it's using to combine in a compound? We use these Roman numerals, and these are just a selection of them, to identify what charge it has. So if it was 2 plus, we'd use the Roman numeral 2. If it was 4 plus, we'd use the Roman numeral IV. Again, we name the metal as is. We change the ending of the second name to "ide," but we have to figure out what charge it has and use that appropriate Roman numeral to show its charge. So when we're writing our formulas, the charge of the metal is always given by the Roman numerals in parentheses. So this is actually easier than what we had before. Before, when we're talking about regular metals, we had to go to our periodic table and search, see what group it's in. But in this case, it's given to you right now in the Roman numerals. We still have to figure out what the oxidation state of the anion is, and again, we go to our periodic table to find that out. We cross down and we reduce and we rewrite, not writing any ones. Remember that polyatomic ions will only have brackets if the subscript is bigger than 1. So let's convert these names into formulae. So the first thing we want to look at is changing the names into symbols. So mercury is Hg, so we'll put Hg, and bromine, bromide, will be Br. Now right away I know what the charge of mercury is. It's given to me right there, 2. Now is it 2 plus or 2 minus? Well, remember that metals lose electrons, so it's going to be 2 plus. Now bromine, we can find right over here. It's in group number 7 or 17. It only has to gain 1 electron. Remember, it's a non-metal, so it's going to gain 1 electron. If it gains 1 electron, it's going to be 1 minus. So once again, we cross this down here, and we'll get Hg1Br2. However, remember that we don't write the ones. So I'm going to rewrite it and say it's going to be Hg(Br2). Copper 1 sulfate. So once again, I'll start off with my symbols. Copper is Cu, and sulfates, you have to remember this one, SO4. Now, again, I know what the charge of copper is right away. I know it's going to be 1, given to me by the Roman numeral. See how easy it is? So we have 1, and because it's a metal, it's going to be plus. Sulfate, we have to remember, it's going to be 2 minus. So again, we bring this to over here. We bring this 1 outside of the SO4, and I'm just going to rewrite it right away and simplify it. It'll be Cu2SO4. Now we know that the outside will have a 1, but I don't write it, and because it's 1, I don't need brackets either. So it's going to be Cu2SO4. Now finally we have iron 2 oxide. So again, we'll start off by writing the symbols. It's going to be Fe and O. Now right away I know that iron has a charge of 2. Because it's a metal, it's going to be 2 plus because it loses electrons. And oxygen, we have to look. So oxygen is in group number 6. It's 2 steps away from having that noble gas configuration, so it's going to gain 2 electrons. If it gains 2 electrons, it's going to be 2 minus. So once again, we're going to cross this here and cross that over here. So what we'll get is we'll get Fe2O2. Now once again, we can see that there's a common factor. We can divide both by 2, and our result will be FeO. So go ahead and stop the video again. Try to convert these names into the formulas. Really be cognizant about where you're getting these charges of the nonmetals. If it's a polyatomic ion, for example sulfate, you'll need to know what charge that is through memory. You won't be able to find it here. But if it's simple elements like oxygen, you'll be able to find it on the periodic table. Remember that these charges are the charges of the metals. Alright, have fun, pause the video, and we'll come back with the answers. Alright, folks, so here are your answers. There are a couple things that really need to be simplified. So for example here, we had 4 outside the bracket and 2 by the SN. Again, there's a common factor of 2, so we factored it out. In case of PbO2, the same thing, we factored it out, as well as tungsten 6 carbonate. So we had 2, we had 6, we had a factor of 2, so it became WCO3. So naming them is a little bit more challenging because we have to figure out what Roman numeral to use. Now once again, when you're going through this, you should go through that flow chart. Is it ionic? Is it made in metal, non-metal? Yes. Then figure out what metal it is. Is it multivalent, aka is it found in the pore or transition metal section? Or is it a normal metal found in group 1, group 2, or is it aluminum, zinc, or silver? Now if you figure out that it is a multivalent metal, you're going to have to determine the charge. And we're going to do this by upcrossing. So we actually convert the subscripts into the charges above the species. The next thing we have to do, and this is the really important part, is compare the value of the nonmetal to the known value of that nonmetal. Now if it's a nonmetal from the periodic table, we look to the periodic table. If it's a polyatomic ion, we're going to have to figure it out from memory. If the value is the same, then we don't really have to do anything. The charge that's above the metal is the charge of the metal. However, sometimes it's different because remember that we simplify some things. So if it's not the same, we're going to have to multiply it to get it to that same value, the known value. But what we do to one side, we do the other side. So that means if we multiply the non-metal, we'll have to multiply the metal. And then that new charge on top of the metal is the actual charge of the metal. And we'll put that into Roman numerals, again using the same rules, changing the ending of I to of the second one to I'd. So let's see an example here. So here we have Ni2S. So what we have to do is we first see that this is a metal, nickel. It's on the left side of this little staircase. It's right over here. And we have sulfur, which on the right side of the staircase, it's right over here. So that is a metal and non-metal. We know it's ionic. Nickel is found in the transition metal, so we can assume that it's going to be multivalent. It's not one of our exceptions like zinc or silver, so we're going to assume it has more than one charge. This means we need to figure out what the charge of that metal is. And the way that we do that is by taking these subscripts and upcrossing them. This has a subscript of 1 because there's no subscript, so we'll bring it up on top of the metal. So if I rewrite this, I have Ni and S. I'm just going to separate them to give me a little more space. The subscript that went here, okay, to form the new charge is 1. And because it's a metal, it's going to be 1 plus. And the 2 went above the sulfur, and because sulfur is a non-metal, it's going to be 2 minus. So now what I have to do is I have to compare this charge of the non-metal to a known charge. Now because it's a simple element, I just have to look at the periodic table. Here I find sulfur. Now what's the charge on sulfur when it combines? Well, it's in group number 6, and it gains electrons, so it's going to gain 1, 2. Awesome. So the charge on the periodic table of sulfur is -2. The charge that we got from the formula is also -2. So what this means is that the charge of the metal is in fact +1. So when it comes to writing this, we'll write nickel. In Roman numerals, we'll put the charge of the metal, which is 1. That's the charge that we found right here. And we continue. So it's sulfur, but we change the ending to "ide", so it's going to be sulfide. Now for our American viewers, sulfide is spelled PH in Canada and in the Commonwealth. For you guys, it would be SULFIDE. So let's look over here, PbO2. So once again, I'm going to move the subscripts up as charges. So the subscript over here by Pb is 1. So I'm going to move that above the O, and the subscript about O I'm going to put on top of the Pb. So I'm just going to rewrite it again. So I'm going to put Pb and O separated. So again, the charge beside the O went up on top of the Pb, so it's going to be 2, and because it's a metal, it's 2 plus. And the charge on top beside the Pb over here went on top of the O, and that's going to be 1. It's a non-metal, 1 minus. Now, if you're observant, you can see the problem already. We have to compare this charge of the non-metal to the known value. So again, we look at the periodic table and we see oxygen is right over here. Again, it's 2 steps away from getting that noble gas configuration. It has to gain 2. So the charge here is actually 2 minus. Here it says 1 minus from the formula. Periodic table says it should be 2 minus. So this formula must have been simplified. Now to unsimplify it, we need to get this non-metal value to its normal charge, which is 2 minus. So what do I do to 1 minus to get it to 2 minus by multiplying? I multiply it by 2. So 2 times 1 minus will give me 2 minus. Now what I do to one side, I also do to the other side. So what that means now is that my charge here is going to be 2 minus, which is awesome. That's the charge that we need. But more importantly, we don't really care that. We just use that to compare. The charge of the metal is going to be 4 plus. That is the charge that lead has. So in this case, it's going to be lead, in brackets, the charge of the metal, which in this case is 4 plus, so IV, and then oxide. That's it. So for our last one here, CO3. So CO is cobalt. I'm just going to write them out. And then CO3 is carbonate, CO3. Now the charge beside cobalt is 1. Okay, we don't have any subscript, so we'll bring that on top of cobalt or carbonate. So that's gonna be 1 minus. But one thing you have to be careful of is this is not the subscript of that came from CO. This is actually still part of CO3. The subscript that came from CO is outside of these brackets, and if we don't see it, that means that is number 1. So that is going to go over CO. Now again, we have to compare the charge of the nonmetal. In this case, the nonmetal is this polyatomic ion. So from memory, what we know is that the charge of CO3 is not 1 minus, it's actually 2 minus. So I have to multiply this to get that to 2 minus. That will become 2 minus. But more importantly, again, I have to multiply this side as well, right over here, and I'll get 2 plus. So the charge of cobalt is 2 plus. So I'll write it cobalt in brackets, II, and carbonate. Because it's a polyatomic ion, it doesn't change its ending. So try to practice, pause the video, and deduce the names from these formulas. Okay? Go ahead and pause the video now. Alright folks, welcome back, and here are your answers. Please check that you got them right. And let's continue. So that's it, everyone. Thanks very much for watching. See you next time.